Work. In the previous video, we have seen that work is done when a force moves the object in the direction of the force and is given by the product of the force and the distance moved in the direction of the applied force. The forces were applied in the same direction we wanted to move those bodies. But in this video, we will see how to calculate work when the force on an object and the object's placement are in different directions. Thanks for watching this video, and don't forget to like, subscribe to the channel and activate the notifications. It is very important to the continuity of this channel. Suppose that the force F moves through a distance d which is at an angle theta to F, as shown below. The work done by a force is defined as the product of the force and the distance moved in the direction of the force. In other words, work is done when the point of application of a force moves in the direction of the force. Therefore, when the force on an object and the object's placement are in different directions, only the component of the force that is in the direction of the object's placement does work. In this example, only the horizontal component of the applied forces causes a displacement and does work. So let's find the horizontal component of the applied force. This component is F cosine of theta. And so we replace F cosine of theta with F sub x, and mathematically work can be expressed by the following equation. F is the force, d is the displacement, and the angle theta is defined as the angle between the force and the displacement vector. Perhaps the most difficult aspect of the above equation is the angle theta. The angle is not just any angle, but rather a very specific angle. If the angle between F and D is 0 degrees, the force and the displacement are in the same direction. Then positive work is being done, and all of the efforts move the object. In this case, the object on which the force is applied gains energy. If the angle between F and D is 180 degrees, the force and the displacement are in the opposite direction. Then negative work is being done. This means that energy is transferred in the opposite direction, and the object on which the force is applied lost energy. If the angle between F and D is 90 degrees, the force and the displacement are at right angles to each other. Forces perpendicular to the direction of motion do not do work. This means that no energy is transferred in the direction of the force. This may seem rather irrelevant since, at first sight, a force at right angles to a direction of travel seems impossible. However, the force of gravity on the Moon, as it orbits the Earth, is at right angles to the Moon's direction of travel. Despite the large gravitational force the Earth is exerting on the Moon, the distance moved by the Moon towards the center of Earth, that is, in the direction of force, is 0. The work done by the Earth's pull on the Moon is 0 because the Earth is not doing any work on the Moon. And so the Moon moves at a constant speed for a very long time. A force of 15 newtons is applied to a block, pulling it 150 meters along the ground as shown below. How much work is done by the force? Analyze the question to determine what information is provided. The force applied is 15 newtons. The distance moved is 150 meters along the ground. The angle between the applied force and the motion is 30 degrees. In this example, the force is not in the same direction as the movement. We substitute the values and calculate the work done. Note that the answer is positive as the horizontal component of the force is in the same direction as the motion. The figure below shows a boy taking a dog for a walk. Calculate the work done by the forces shown when the dog moves 20 meters forward. Analyze the question to determine what information is provided. The force applied is 185 newtons. The distance moved is 20 meters along the ground. The angle between the applied force and the motion is 150 degrees. The cosine of 150 degrees is negative. We substitute the values and calculate the work done. The horizontal component of the force is opposite to displacement. Therefore, the answer must be negative. A 120 kilograms crate is dragged along the horizontal ground by a 300 newtons force acting at an angle of 60 degrees to the horizontal, as shown below. The kinetic frictional force is 100 newtons. Find the work done by each force acting on the crate and the total work done by all the forces when the crate slides for 2 meters. We first calculate the work each force does. The force F is 300 newtons and the angle theta is 60 degrees. The work is positive. The force of friction is 100 newtons. The angle between the force of friction and the motion is 180 degrees. The cosine of 180 degrees is -1, so the work is negative. The work by the weight is 0 because its direction is perpendicular to the displacement. For the same reason, the work by the normal force is also 0. Note that we don't need to calculate the magnitude of the normal force to conclude this. The total work done on the crate by all forces is the algebraic sum of the work done by the individual force. If many constant forces are acting in an object, we can find the net work done by finding the net force. We first draw a free body diagram showing all of the forces acting on the crate, and we choose a coordinate system. Find the components of the force F. Newton's second law tells us that because the crate's motion is purely horizontal, the net force can have only a horizontal component, that is, F sub x minus the force of friction. The total work is therefore the work done by the x component of the resultant.